Okay. All right, we're going to go look at calculating delta S. We talked about delta S, which is entropy, in the last little section, and we talked about the fact that the entropy of the universe has to be greater than 0 for this to be consistent with the second law of thermodynamics. Okay? Now, we talked about the fact that there's 3 things up here that denote an increase in enthalpy. One is a change in phase from solid to liquid, or liquid to gas, or solid to gas, moving in that direction. Or an increase in temperature will also add an increase of disorder because you're adding more energy to the system overall. Another thing will add an increase in entropy is simply having more matter, right? So if I had 2 moles of something versus 1 mole of something, if I have 2 moles of sodium chloride in the solid state, that's going to have more disorder, more entropy than 1 mole of sodium chloride in the solid state, because there simply is more matter, so that's going to have more disorder. Which takes me to one really important fact about entropy, and that is that all matter has disorder associated with it. So when we talked about enthalpy of formation and the fact that it doesn't take any energy to form things that are in their natural elemental state, right? The fact that oxygen gas, O2, in its elemental state has no change in energy of formation. That is not true for entropy. All matter has a certain amount of disorder that's associated with it. So whether you're talking about something that's in its elemental state or in a different form, it always has some level of disorder associated with it. Okay, so now we're going to get on to identifying whether a chemical reaction has a positive delta S. Remember, we want our delta S of the universe to be greater than 0. Okay? So remember, I have 3 equations up here, or 3 chemical reactions that we're going to look at quantifying. Is this a positive delta S? Does it have a delta S that's greater than 0? And what we look at is we look at the number of moles on each side of the chemical reaction, and then we look at the phases. So I'm going to go ahead and look at letter A up here. Okay? So in letter A up here, we have on the reactant side, here's our reactants, I have 1 mole. That's A, and again, we're wanting it to go from less disorder to more disorder. That makes our delta S positive. So I have 1 mole of a solid, and I have 1 mole that's aqueous. And what does it mean for it to be aqueous? It means it's in its liquid form. It's just dissolved in water, okay? Now, let's compare that to the disorder on the reactant side. And on each one of these have 1 mole. So on the reactant side, I've got 1 mole that's in the aqueous form, and I have 1 mole in the gaseous form. Okay? So when I compare those, am I going from less disorder to more disorder? I am, because if these kind of cancel each other out because they're both moles in the aqueous form. You see we have 1 mole of solid on the reactant side and 1 mole that's gaseous on the product side. So this would have a different color pen. This would have a delta S that is positive. This is consistent with the second law of thermodynamics. Delta S is greater than 0 here. Let's go ahead and look at this second one and compare what we've got, okay? So on the second one here, on the reactant side, I've got 1 mole that's gaseous and 3 more. So I've got a total of 4 moles that are gaseous, okay? And when I compare that to my product side, I've got 2 moles that are gaseous, okay? So when you think about that, you've got more matter that's moving at with a higher amount of disorder, moving to less matter at the kind of the same level of disorder. So this actually would have a delta S that is negative. We're going from more disorder with 4 moles to less disorder with 2 moles. So this would actually have a delta S that is negative, okay? That is not consistent at whatever temperature this was run at with the second law of thermodynamics, okay? And finally, we have this third one down here. Let's compare those numbers, okay? So I've got 1 mole that's aqueous, I've got 1 mole that's solid. Okay, and on the reactant side, sorry, the product side, I've got 1 mole that's aqueous here. I've got 1 mole that's liquid, so that basically gives me 2 moles, right, in the liquid phase. And I've got 1 mole that is gaseous. So that means I'm going from 1 mole aqueous, 1 mole solid, to 2 moles liquid, this is also liquid, and 1 mole of gas. So clearly we're going to have more disorder on the product side of the equation. So again, this would be the same as letter A up there. This would have a delta S that is positive, okay, that is consistent with the second law of thermodynamics. Okay, so that's how you can look at it kind of qualitatively and just determine, is it consistent? Is delta S positive or negative? We do also have an equation that allows us to calculate a particular delta S. Okay, so and that is just this equation where again you have to use the table, you have to look the numbers up as you would take to find the delta S of a reaction. You're going to take the sum of the delta S of the products and subtract. Hello, Trevor. We're going to subtract the sum of the delta S of the reactants. Okay, thank you very much.